Good morning, all of you. Today, we are going to discuss about mechanical properties of fluids in session 3. In that, mainly, we'll discuss about variation of pressure of a liquid column, when it is accelerating vertically upward or vertically downwards. In the last session, we discussed about variation of pressure, hydrostatic pressure due to depth h. So that we discussed as rho is equal to rho naught, P is equal to P naught plus rho gh is equal to P naught plus rho gh. So the pressure variation is independent of mass, depends only density, height, and acceleration due to gravity. Suppose you can take this example. So we can understand. So in this example, I will show you how the pressure will be same. Suppose you can take this example. We are talking about variation of pressure with the depth. That we already understood. P is equal to P naught plus rho gh. Suppose you can take 3 tumblers or 3 beakers of different shape. Let us take like this. Let us take like this. Let us take like this. And fill the liquids for the same height. Fill the liquid for the same height. You can observe that base area will be same in all the cases. So let us say tumbler A, B, C. The height of the liquid here same h. So you can observe the pressure at A, bottom of this A, PA, pressure at bottom of B, PB, pressure at the bottom of C, PC, bottom of this, due to this liquid. So above the pressure we have P naught, atmospheric pressure. Here also P naught, here also P naught. Then the pressure at A, PA is equal to P naught plus density rho GH, height of the liquid. So let us say rho be the density. All the liquids is same, let us say water. So here you can observe PA is equal to P naught plus rho GH, or PV also you can take P naught plus rho GH, because same height, same liquid density. PC is equal to P naught plus rho GH. G also same. So from this it is understood that PA is equal to PB is equal to PC. Okay. So this is one example. Next, what about weight? Let us say weight of the liquid is WA. In tumbler A, weight of the liquid is WB. Weight of the liquid is WC. Will this weights is same? Means no. Here you can observe here liquid is less compared to B, then W is less than WB, WB less than WC. So WC is the heaviest part. So even though weights are different, but pressure at the bottommost point will be same in all the 3 cases. So this is the criteria paradox you can see here. Okay. Similarly, you can take irrespective of the shape. It is observed that the shape of these 3 beakers or tumblers are different. Okay, irrespective of the shape, and pressure is independent of the shape of the containers also we can observe here. It depends only density, acceleration due to gravity, and height. Okay, right. Next we will see variation of the pressure fluid pressure or liquid pressure pressure when liquid is accelerating vertically upward or vertically downward. Liquid or fluid accelerating. Okay, with some acceleration A. So in this case, the acceleration will be either vertically upward or vertically downward or horizontally. There are three cases will be there. We'll see one by one. Suppose if it is accelerating vertically upward, what happens? Vertically upwards. So let us consider a beaker of liquid. Here you can observe. So this is the liquid column. Here above pressure is very common. P naught is acting, atmospheric pressure. In this, let us imagine cylindrical column of liquid, imaginary cylindrical column of liquid. Imaginary cylindrical column of liquid. So above, let us say point P at the center surface. Here below, let us say point Q. Okay. Then let us say due to above liquid a force F1 is acting vertically downward. Due to below liquid at this point Q, force F2 is acting. Okay. Force F1 we can say acting here at point P. Force F2 is acting at this point Q. So let small m be the mass of the liquid within the cylindrical container, imaginary cylindrical shaped liquid column. Then mg is acting vertically downward here, mg. Okay. Let us say P1 be the pressure at point P and P2 be the pressure at point Q. Okay. And let us say height of this liquid column is h. H is the height of the liquid column. Okay. Then you can observe the forces. The total system is moving with an acceleration A vertically upward. Okay. Then the forces acting at the bottommost point Q and uppermost point P you can see. Force acting at the uppermost point is that force F1 is equal to P1, pressure P1 into A, area of cross section. Let us say area of cross section is capital A. For this cylindrical column, cylinder face area is capital A. Similarly, force acting at the bottommost point is force F2 at point Q. This is at point Q. That is P2A. Okay. And mg, height of the liquid acting vertically downwards. Okay. So that m also you can write m is equal to mass of the liquid, density rho into volume of the liquid. So the density rho into volume you can write as h, height of the liquid into area of cross section A, rho HA. Okay. Now net force you can write F2 vertically downward upward minus F1 vertically downward plus mg vertically downward. F2 minus F1 plus mg, that is the net force. According to Newton's second law, net force is equal to ma on this imaginary cylindrical column. F net is equal to ma. Okay. So you can substitute this F2, F1 and m value here. F2 is P2 into A minus F1 into P1 into A plus m is rho A into H into G is equal to ma, rho A into H into A. So here A is common, you can observe both sides. They can write pressure difference P2 minus P1 minus this A is common, you can cancel, minus rho Hg is equal to rho Ha. Okay. They can expand this relation. Here you can write P2 minus P1 is equal to rho H into G plus A. Rho H into G plus A. Are you clear this? So this is the pressure difference due to liquid column is moving upwards with an acceleration A. It is something like the lift is moving upwards. In that case, we discussed the effective acceleration is G plus A for inside body. Similarly, the container is moving upwards like a lift. In that case, the effective acceleration due to gravity plus acceleration is G plus A. It is P2 minus P1 is equal to rho H into G plus C. Okay. So this is about vertically upwards. Suppose if it is vertically downwards, very simple. Okay, the G plus A will become G minus A. So if the liquid column is moving or accelerating, if it is accelerating vertically downwards, then we can write the pressure is equal to pressure difference P2 minus P1 is equal to rho H into G minus C. Okay, the pressure difference you can write rho H into G minus C. I hope this understood all of you. Okay, if it is vertically moving upwards, pressure difference will be P2 minus P1 is equal to rho H into G plus A. If it is accelerating downwards, P2 minus P1 pressure difference is equal to rho H into G minus A. Okay. Next, if it is accelerating horizontally, then what is the pressure difference you can see. Okay. So this is about second case, accelerating vertically downwards. Next, we'll see third case. If liquid column is accelerating, liquid is accelerating horizontally. Horizontally. It's some acceleration A. Acceleration A. So let us draw the diagram again. A container with a liquid. Container with a liquid. It's some acceleration A horizontally. Here, if it is accelerating horizontally, what happens? The liquid is same horizontal level. Means no. The liquid will go back slightly like this. Like this, the liquid will move back side. Because of pseudo force acting on that liquid, there is a chance to move like this. Okay, you can observe here. So in this situation, there is a height difference will be established between the front end to back end of the liquid. So let us imagine first imaginary column of liquid, like a cylindrical column of liquid I am drawing. Here I am drawing cylindrical column of liquid. So let us consider here area of cross section A, capital A, same. Here instead of height, we can say length of the liquid. Length of the liquid column is L. So the area of cross section is, let us say point P towards left side, point Q towards right side. Point P, point Q. Now you can observe at point P and at point Q, above is P0 is the atmospheric pressure will be already there. Now this is at a height you can observe. Let us say at point P is at a height of H1 from the free surface of the liquid. Point Q is at a height of the center of point Q. Center of point P is at a height H1, the center of the phase surface. And here it is at a height H2. This is H2 height. The center of the phase, point Q, that is at a height of H2. Okay, that is the difference you can observe. Then effective height also you can draw here. The height difference or effective height here. You can see this one, horizontal line. This horizontal line you can see here. This is the horizontal line. That means therefore to height difference you can see here h1 minus h2, that is h here, height difference. And here this height difference making a certain angle theta here. H is making certain angle theta. Okay. So this is about the total diagram. Now you can show the net force acting on the system how it is. So at point P, what is the pressure value you can see. At point P, let us say pressure, you can take H1, then P1 you can take. At point Q, P2. Okay, so the symbols are usual, there is no problem here. So in this case, it will come like pressure difference, you can see. Then I can see one by one, I can write the pressure P1 value. First of all, the force value you can see here, force acting at point P, because of it is moving towards right. It's moving like this. Then here you can imagine at point P, the force acting towards right. Let us say F1. Here due to this liquid, the force acting, let us say F2. Okay. Then what is this F1 value? Force acting at point P. Force acting at point P on the liquid horizontal level is F1. F1 is equal to, let us say, P1 into area A. Similarly, at point Q, oppositely it is acting F2. F2 is equal to P2 into area A. Okay. Then now net force what you can write? Here F1 is greater than F2 because it is moving towards right. So that F1 minus F2 net force is equal to MA, mass of the liquid. Let M be the mass of this cylindrical column. Okay. And M also you can write density into volume. So density into volume means area into length, rho AL. Then F1 is what is the value? P1 into A minus F2 is P2 into A is equal to F net is equal to MA. MA means rho AL into A. Rho AL into A. Okay. Now equation you can write AA cancel. P1 minus P2 is equal to P1 minus P2 is equal to rho L into A. Rho L into A. Okay. So this is about the equation for the pressure difference in the horizontal level where liquid is moving horizontally. Okay. From the left side column to right side. In terms of height, if you can see here pressure P1 what you can write. Pressure P1 is equal to P0 plus the point P is located at the height H1. P0 plus rho G H1. Similarly, P2 is equal to P0 plus rho G H2. Okay, then P1 minus P2 is equal to P0 cancel. Rho G into H1 minus H2. Okay, then from this you can write P1 minus P2 is equal to rho G into H1 minus H2. Then you can substitute this as equation 1 and equation 2. P1 minus P2 equal, then rho G into H1 minus H2 is equal to rho LA. Then rho cancel. Then H1 minus H2, H1 minus H2 is equal to L into A. From this you can write A is equal to H1 minus G is there now. Rho G. Rho G H1 minus H2 is equal to G will be there. G into H1 minus H2 is equal to L into A. Then H1 minus H2 is equal to H1 minus H2 by L is equal to A by G. A by G is equal to H1 minus H2 by L. So from this diagram, you have a theta here. Theta means this is the triangle you can see here. This triangle. Triangle what is showing? This opposite side is H. That H you can say H1 minus H2. Okay, this adjacent side is L. You can see our length of the cylinder L. This also L. Then you can write tan theta from the straight angle triangle H by L. That is equal to H1 minus H2 by L. So from this you can substitute. Here H1 minus H2 by L is equal to tan theta. So therefore A is equal to A by G is equal to tan theta. That means A is equal to G tan theta. You can write A is equal to G tan theta. This is one relation we can establish. The acceleration of the liquid making an inclination theta. In that case, acceleration A is equal to G tan theta. Okay, this is the one relation we can establish if the liquid is accelerating horizontally. I hope this understood all of you. Right. Next, we'll see one more topic. The net force or average force acting on the liquid column due to pressure difference. Average force acting on liquid or fluid column due to pressure differences. So let us consider a vertical column of liquid. You can draw this diagram. Okay. In this liquid container, I can take. In this, you can take an imaginary cylindrical column again. Imaginary cylindrical column. So topmost point is, let us say, point P. Bottommost point, let us say, point Q. Area of cross section, let us say, capital A. Area of cross section, let us say, capital A. Then here, the point P is at a height H1. You can imagine from free surface. This is the free surface of the liquid. Above, you can expect P0 is the pressure, atmospheric pressure. Then this bottommost point is at a H2 height, H2 depth, sorry, to depth from the free surface of the liquid. Uppermost point at a depth H1 from the free surface of the liquid, and lowermost point at a depth H2 from the free surface of the liquid. Then due to that, there is a pressure difference, we understood. Then in that case, because of this pressure difference, there is an average force acting on this liquid column. What is that average force? So you can see here. So the bottommost point is at pressure P2, uppermost point is at pressure P1. Okay. Because of this depth difference, then P1 is equal to, we know already, P0 plus rho G H1, where H1 is the depth, rho is the density of the liquid. P2 is equal to P0 plus rho G H2. Okay, then P average, you can say P average is equal to P1 plus P2 by 2. Okay, P average, the average pressure. Then this P average pressure you can write only due to depth variation, the average pressure you can say. So rho G H1 plus rho G H2. P0 will be there always. P0 is outside pressure plus rho G H1 plus rho G H2. P0, P0, 2 P0. Rho G H1 plus rho G H2 by 2. This 2 P0 by 2 is P0 plus rho G H1 plus rho G H2 by 2. So this P0 is common due to this liquid column. P0 will act both upside and bottom side. Then the average pressure only due to depth variation you can take. Only due to depth variation. Rho G H1 plus H2 by 2 only you can take. Rho G H1 plus H2 by 2. Okay. Rho G H1 plus H2 by 2. rho G into H1 plus H2 by 2. This is only because of liquid column height difference. Then you can say here, average force or net force acting on this is F average is equal to P average into area of cross section of the liquid column. P F average is equal to P average into area of cross section. Okay. Then P average is rho G into H1 plus H2 by 2 into area. So F average is equal to rho G into H1 plus H2 by 2 into area. Okay. So this is of the average force acting on the liquid column because of the pressure difference. Okay, from the topmost point to bottommost point. Okay. So this is not created by external pressure P naught. This is only because of the height difference or depth difference we have discussed. Okay. So this is about end of the today topic. So what we discussed, I will recap. We discussed about variation of the pressure with the depth with an example. And then if the liquid column is moving accelerating vertically upwards, what is the pressure variation? P2 minus P1 is equal to rho H into G plus A. If it is vertically downwards, so P2 minus P1 is equal to rho H into G minus A. If it is horizontally moving, then you can write P1 minus P2 is equal to rho LA. And we have related A is equal to G tan theta if it is making certain inclination. And average force acting on the liquid column due to pressure variation. Okay, thank you, Ananda.